Okay, this is the lecture video for MAC 1105 College Algebra. We're still in section 5.1 where we're looking at exponential functions, and we continue in this video with examples 13 through 19. Okay, so in example 13, we begin to look at solving exponential equations. And the key to many of these equations is to get both sides of the equation to have the same base. And once you get them to have the same base, you'll be working with just the exponents, because the only way that two exponential expressions can actually be equal is if their base and their exponents are the same. And I'm going to demonstrate that in each of the problems. For instance, in this particular problem, the base is 64. It is written as an exponential expression. It's 64 to an exponent of x. This side is not even written as an exponential function, so the key is to get this rewritten as an exponential function where the bases match. So we have to think of various ways that we can write 64. Like, for instance, you can rewrite 64 as 4 to the third using a base of 4. But can you rewrite this using a base of 4? There are also other ways to rewrite 64 as a base and an exponent. We're looking for a base that these two have in common. Because with the present base that it has right now, you're not going to get a 128. In other words, 64 to what power? You could try raising it to the first power, it would be a 1. You could try raising it to the second power, and it's already too big. So you can't use the same base that you're seeing here, and that's why I'm trying other bases right now. So let's see. I know that 4 to the third will get me a 64. Okay, let's see if I can make 128 out of a base of 4. So it's obviously bigger than 64, so let's see, 4 to the fourth, too big. So 4 is not going to work. It works to get a 64, but you can't make a 128 out of a base of 4. So let's go with a different base here. How about a base of 2? Let's see if I can get a 64 out of that. 2 raised to the fifth is 32, too small. 2 raised to the sixth, 64. So I can rewrite this 64 as 2 to the sixth with this base and this exponent. So this is my 64. That 64 was raised to a base of x. Let's see if I can also write the 128 with a base of 2. So let's see, 2 to the 6th was 64, so how about 2 to the 7th? Let's see what we get from that. So there we go, right there. 2 to the 7th is that 128 that we get. Now we want the bases to match exactly before we can go on to the step where we can basically disregard the bases and just work with the exponents. That's how we'll be finishing the problem. But you can only do that once you get to the point where these bases match exactly. And right now this has a base of 2 to the 6 on the x. This is the base of the x, whereas this just has a nice clean 2 as the base. So what you're going to do is you're going to mingle these two exponents. This is called raising a power to another power, and when you're doing that, you multiply. So on the left side, you have 2 raised up to a power of 6 times x. So now you have a nice clean base of 2, exponent 6x. And on this side, we have a base of 2, exponent of 7. Once you get these bases to match exactly, then you can create an equation where you're working with just the exponents. Because again, the only way that two exponential expressions can be completely equal is if their bases match as well as their exponent. So now you're going to go into the equation where you're working with making the exponents match. The bases already match, now make the bases match, or in other words, make them equal. And so that's why you're solving this equation, to find the value that does make them equal. What x value would make this exponent equal to this? So just divide by 6, and you have x is equal to 7 sixths. If you were to put 7 sixes in there, this exponent would be a 7, just like this exponent's a 7, and the bases already match. So you will finish these problems by working just with the exponents. Okay, likewise in this problem. Right now this has a base 2, it can't get any smaller than that. So we're going to rewrite this as a base of 2. So this will be 2 to the 4th. That's how you get a 16. This one is 2 to the 4 to an exponent of 4x minus 12. Okay, again, once you get those bases to match, now make the exponents match. And you make them match by setting them equal. So it's going to be 4x minus 12 is equal to 4. And continue solving that until you find the x value that makes this exponent match this one. So we're going to add 12 to both sides. That'll give us 4x equal to 16. Divide by 4, divide by 4. And you end up with x equal to 4. And that's your final answer there. Okay, moving on to example 15. In example 15, you start off with, let's see, a base of 4 with an exponent of 7 minus x. This has a fractional base, and we really can't go on unless we make this base match this. So let's see, we can make a 64 out of 4, a 1 over 64 out of 4s. First of all, let's just address how do you get 64? That would be 4 to the 3rd. But since this 64 is happening in the denominator, that would have to be 4 to the negative 3rd. This is equal to, this portion right here, this base is equivalent to this, 4 to the negative 3rd. If the 64 would have been up top, then it would have just been 4 to the 3rd. But because it's in the denominator, things that are in the denominator, when they're in power form, they get expressed with negative exponents. So there's your 1 over 64 raised up to a power of x plus 5. So we've got a double exponent here, and anytime you have that, you want to use power to a power so that you just have a single exponent rather than one power on top of another. Okay, so this is going to be now 4 to the negative 3 times x. You're doing power raised to another power, which calls for multiplication of this power with this power. So that'll be negative 3x minus 15. Whereas what's on the left side just stayed the same the whole time. I haven't done anything to it, but I now have the bases matching. Write a little bit clearer here. So this will be 7 minus x. Okay, so note that those bases match, and once I get to that point, I can work just with the exponents. Okay, that brings me to this equation, and then I'm going to solve for x. So I'm going to bring my x's over here. This would become positive 3x as I bring it to the left. That's the same thing as adding 3x, adding 3x. So this is no longer on the left, it's over on the right as a positive 3x, and at the same time I'm going to move the 7 over here, which makes it become negative 7. Okay, so I have negative x plus 3x, that's 2x, and then on this side what I have is negative 22. Negative 7 combined with negative 15 is negative 22. I'm going to divide by 2 on both sides, and that'll leave me with x is equal to negative 11. And that's your solution for that one. Okay, example 16. I have 25 to a power of x plus 2. We might be able to make this out of 25s, and if we can't use 25s to create this, then we could always go down to 5 and use that as a possible base. Okay, so let's see what we can do. 25, only because this has a base of 25, 25 squared. Yep, that's 625, so we can go with the 25s. This already has a base of 25, and this can be rewritten. So 625 is the same thing as 25 squared. So that's your 625, and that 625 already had an exponent of x minus 7. So we are trying to raise one power to another power requiring multiplication. So it's going to be 2 times x, because that's the power to a power rule, that when you're trying to multiply, when you're trying to raise one power to another power, you multiply the powers. So this side becomes 25, but now with a single power of 2x minus 14, instead of having a two-step power. And then this one is 25 to a power of x plus 2. And once the bases match, you can discard the bases and work just with the exponents at that point to get them to match. They need to be equal also. Okay, now solve for x. I'm going to bring this x over here, at which point it will become negative x, and I'm going to bring the negative 14 over here, at which point it will become positive 14. Okay, so 14 plus 2, 16. 2x minus 1x, 1x. And you're already at 1x equal to 16, so that is your solution. I'm just checking my arithmetic there. So yeah, we moved the x, that was 1x. We moved the 14, yep, 14, 16. Okay, now moving to this one. So this has a base of 4, suggesting that a possibility for 1024 might be using a base of 4. Let's see if we can create a 1024 out of 4. So 4 raised to the 4th is 256. 4 raised to the 5th is, there we go, right there. 4 raised to the 5th is how we get that 1024. Whereas on this side, it's 4 to the 4v plus v squared. Okay, bases are the same, therefore we can discard those bases and right now just try to make the exponents equal. So this is 5 is equal to 4v plus v squared. So we're trying to figure out what values for v are going to work here, and since it's a second degree equation, you need to bring everything to one side and factor. So I'm going to bring this over here, at which point it would be your squared term, your first degree term, and your constant, all zeroed out and ready to factor. Okay, this will be we're going to use the guess and check method, and that's because these coefficients and the coefficient here and the constant here, namely because this is a 1 and because this is so small, you can go with guess and check rather than splitting the middle term. Guess and check, you just have to know your times tables. Just look for two numbers that multiply to give you this C value of -5. But those two values that you come up with as multipliers to get -5, they must add to give you this B value right here, the coefficient of the first degree term. So that B value is 4. Easy enough to find. Just 5 times 1, one of them is going to have to be negative. And you can tell which one has to be negative by the fact that you need to get a positive 4 when you add them. Therefore, the bigger number must be positive, smaller number has to be negative. That times that is -5, that plus this -1 is 4. Okay, larger number will bear the sign on the sum or difference. Okay, so we know that 5 and -1 are the numbers that will get this trinomial, second degree trinomial factored. So you need these at the front and then these numbers 5 and -1. It doesn't matter which one you put in the first parenthesis or which one you put in the second parenthesis. Okay, the solutions to this equation are also called zeros. So in other words, what makes this 0? This factor right here, v equal to -5. That's one of your solutions. What makes this 0? V equal to 1. So that's another solution. Do they both work? Do both of these answers actually create an equal exponent on both sides? Let's check it out real quick. So 4 times -5 is -20. Just checking it real quick. Plus negative 5 squared, which would be 25. Yep, you'd have an exponent of 5, just like you have an exponent of 5 here. Would the 1 work? Let's see. 4 times 1 would be 4. And then 1 squared would be 1. Yep, that works out too. So your solutions here are actually 1 and negative 5. Both of them work. We're moving to the next section where we have some application. Not the next section, but the next page where we have some application problems. A typical problem when you're talking about exponential functions and applications of those functions would be the compound interest problems. We have compound interest just in general being where you're earning interest on your money, and then in successive, on the first year that you have your money in a bank, and then in successive years or successive compounding periods, the bank is coming in and paying you interest on the money you invested plus the interest that you earned from them. That's what compounded interest is. You're earning interest on your interest. And so we have a certain type of compound interest where the number of compounding periods are suggested by how often the bank goes into your account and pays you interest. So you could be compounding semi-annually. That means you're being paid interest on your interest twice a year. You can be getting interest quarterly, where you're being paid interest 4 times a year. So your interest is building upon your interest on that kind of payment schedule. The bank might be paying you monthly, assessing interest monthly. Sometimes they're doing it continuously, and then you'll switch to a different formula, which I have put for you right here. Okay, but before we start using this formula, this other formula is when you actually know how many times the bank is going to go into your account. It's on a specific schedule that the bank is going to go into your account. That's when you're going to be using this. This has an N in it. This N is for compounding periods. And I'm going to tell you what each of these things stand for. The A stands for the final amount, or the accumulated amount, as they call it, which is just the final amount in your account. Oops. Okay, the P that you see right there, that stands for principal, which is the beginning amount in your account. The A is what it builds up into at the end of it all. So P is the beginning amount, starting amount, whatever you want to call it, same thing. Beginning amount. Okay, the R that you see there, that is the rate of interest. And your rate of interest, whatever the bank happens to be paying you, in this particular problem, it's 7%. That rate of interest must be used as a decimal, as is the case with when you're using any kind of a rate in any kind of algebraic problem. So rate of interest as a decimal. So in this particular problem, we'd be using 0.07. When you're converting a percentage to a decimal, think of the decimal being at the end, slide it 2 places to the left. That's the same thing as going 7 divided by 100, because that is what percent means. Parts out of 100. This is 7 parts out of 100, or 7 divided by 100, 0.07. Okay, the N that you see here, as well as part of the exponent, that N is the number of times that you get interest, which is also known as the number of compounding periods. And then the T that you see there, that's just time in years. It's how much time you're leaving your money in the account. Okay, so let's make sure you're clear on the number of compounding periods. In other words, the N value for parts A, B, and C. Bank's going into your account twice a year. That's what semi-annually means. Semi-annually means, therefore, N is equal to 2 for that problem. Here they're going in quarterly. You'll be using N equal to 4. And here they're going in monthly. Well, you're reacting to these phrases based on what it means, the schedule that it means, it implies per year. So if they're going in monthly, they're going in 12 times per year. If it says quarterly, they're going in 4 times per year. And if it says semi-annually, twice a year. Okay, the actual value that you end up with in your account is called the accumulated amount, and that's what this formula will get for you. So in this problem, we have a principal of $15,000. In other words, the customer starts with $15,000, and I am just plugging into this account that I've highlighted for you here. $15,000 for the principal, and then it's 1 plus the rate divided by the number of compounding periods, which for part A is 2. And then I have a power of N times T. So 2 times, this person is leaving their money in the bank for 4 years. I would clean this up a little bit before plugging it in the calculator. So you would just have 15,000. Let's get one single number for this, and of course you can do the power, you can simplify that power very easily. You want to clean it up a bit before you put it in the calculator. Right now all I'm going to do is get a single number for this. 0.07 divided by 2 plus 1 is 1.035. And then you're going to round these answers to dollars and cents. Now put it in the calculator, the whole thing, 15,000 times 1.035 raised up to a power of 8. And so under those conditions, being compounded semi-annually, starting with 15,000, a rate of 7%, and leaving it in for 5 years, you end up with an accumulated amount of $19,752.14. If anybody then asks another question on top of that, like for instance, how much interest did the person earn? That would just simply be subtraction. It would be what you ended up with, which is your accumulated amount, or in other words, your final amount, minus what you started with, which is this minus this would be $4,752.14. Okay, that's for part A. For part B, now going in quarterly to find that final amount under the same conditions, but getting paid interest upon interest 4 times a year. So it would be 1 plus your rate of 7%, but this time there's 4 compounding periods, so where that N value is, we're putting a 4 rather than a 2. And the power, being N times T, is 4 for N this time rather than 2, times leaving it in for 4 years. So that would be 15,000. I'm going to get a single number for this with a power of 16. 4 times 4 is 16. So this would be 0.07 divided by 4 plus that 1 that's inside the parentheses will be 1.0175. And then popping all of that into the calculator. And you get, this time, $19,798.94. So you make a little bit more. The more often they go into your account and compound your interest, the more you're making. So this is a little bit more than if you were on a semi-annual compounding schedule. Okay, and let's do part C here. For this one, we're compounding monthly, so it would be accumulated amount is 15,000 times, rest of the formula goes 1 plus R over N, the rate over N. This time our N value is 12 because we're compounding monthly, and our power is N times T, 12 times 4. So if we put that in the calculator, but clean it up a little bit before we do so, I'll get just a single number in here. I'll be using a power of 48. So this value that's in here, if I just simplify it, it'll be 0.07 divided by 12 plus 1. And I'm gonna, just for better final accuracy, I'm gonna hold on to 5 numbers after this decimal. 0, 0, 583 I'm gonna hold on to, and then I'll round off more severely in the final answer. Okay, putting all of that in the calculator, now that I've cleaned up what's inside the parentheses, I have 15,000 times 1.00583 raised up to a power of 48. So if they're coming into your account monthly, then you end up with 19,000 as your final amount after 4 years, $827.65. Okay, finally moving to part D, where they're compounding continuously, so you really can't say how many compounding periods there are. They're just continuous. You're just continuously earning interest, and therefore, since there is no specific number of compounding periods, you switch to a different formula that doesn't have N in it. So it's this formula whenever you're doing continuous compounding. And we switch to this formula. All the variables still mean the same thing. Take note that the E is not a variable. P is for principal, R is for rate, T is for time, E is a number that's on your calculator. Okay, so this will be the principal if you're earning interest continuously, $15,000 times E raised up to a power of R times T, which is 15,000 times E to a power of 0.28. That's this times this. 0.07 times 4 is that 0.28. Okay, putting the whole thing in the calculator would be 15,000 times E raised up to a power of 0.28. Close it, and you get 19. Now this is going to be the highest amount because you're earning it more often than in any of the other situations in part A, B, and C. So 19,846 and 95 cents. Okay, and that's parts A through D, all compound interest problems. One more application problem. Exponential functions used very much when studying the growth of a population, the growth of any kind of sample, so very much used in science type problems, studying the population, and that's what this problem is about. It says the city of Fort Pierce has a current population of 45,329 with a projected growth rate of 1.3%. The population of Fort Pierce can be modeled by the following. The population as a function of t, time, is the initial population, 45,329, This is the growth rate right here. That 0.013 is this annual growth rate that it's experiencing. And T is time per year. So it says, what is the predicted population of Fort Pierce 20 years from now? So you would just take this function and evaluate it at a time of 20 years down the road, where this is the initial population, 45,329 times E, raised up to a power of you can put the leading zero if you want to or not, 0.013 times T. And you can get a single power here first if you like, or enter it as is. So this multiplied by that is just 0.26. So we're going to be raising that E to a power of 0.26. So 45,329 times E raised up to a power of 0.26. Close that. And why don't we give the answer as is, and then we'll also give it rounded to the nearest whole number. So this is the exact answer. $58,788.5439. And if we round it to the nearest whole number, it would be 58. $789 people. Okay, that completes the solving equations, exponential equations. Looked at a bunch of different examples of that type, and then also some applications that had to do with exponential functions, and those were the compound interest problems and then an additional application problem. Okay, that completes the lecture for college algebra, MAC 1105 for section 5.1.